Hi, this talk is on our solar PV's capacitive. This talk has been given to NERC inverter-based resource performance working group monthly meeting on July 22nd. This is a video, this is a recording again. My name is Ling Fan. I'm the PI for a project sponsored by Department of Energy Solar Energy Office. And I have co-PIs are listed here, including Zixin Miao Shaohui Shah, Zemo, and Vahan from Rio. Both this project, the entire slides, thanks to both Vito and Cito, wind and solar. The outline of this presentation is first, it has two parts of the show, let's say. The first part of the show is just a direct answer to the question posed. Solar PV is capacitive. So we're going to use just the inverters impedance measurements obtained by the real team. They have a very advanced measurement system, can handle high power devices. And this will give a confirming answer, yes. The second part of the show is on event analysis. We can cover mainly on the subcycle over voltage, but partly also cover AC over current and hydro one's 80 Hz oscillations. Those event analysis are based on a published letter and two submitted letters. So first, let's look at the 1 megawatt BESS system. BESS system. So that is happening, measured by the real team. So in the right, you can see this is the battery system, the positive sequence impedance. So looking at the 60 Hertz, there's a peak. And at 60 Hertz, you can see it is from, this part is already inductive. Right? So that's inductive, that's inductive. So about 60 Hertz to 100 Hertz, this BESS system, you can see it is showing it is inductive. All right, so next we are looking at the first solar PV plant. The vendor one has 440 kilowatt inverters, and total is 160 kilowatt. And the blue line is the vendor two. It is about total is 250 kilowatt. So you can see it actually it is a combination of 4 inverters, a combination of 2 inverters, and overall performance is showing in the below body plot. So these are the body plot magnitude and phase angles. Zooming in, let's look at this 60 Hertz to about 80 Hertz. You can see. So in fact, if you look at the left and the right, then the right is the zooming part. So you can see that at this point that about 60 Hertz to more than like 200 Hertz, right? So this is 200 Hertz, and then this is 300. In fact, from this 60 Hertz to 1000 Hertz, it's all capacitive. And pay attention more to this region. It is not only capacitive, but also it has negative resistance. So this is there's a potential like a sort of like an interaction that you can expect if your grid is inductive and this is capacitive and there's negative resistance. So one example is showing here. Here is the 250 kilowatt. This is the inverter. And the inverter's impedance and the grid impedance are put together. And the crossover frequency is about here, about 150 Hertz. At 150 Hertz, you can see these two, there's the phase angle are pretty large, almost close to 180. So this is basically, you can see this is invite any kind of poorly damped or undamped oscillations based on stability criteria. This guy is basically LG is pretty large. That means the short circuit ratio is pretty small at 1.5. And then you can see this guy is meeting the impedance of the PV. So if it is smaller, then you expect to see more shallow slope. And then at this region, you won't expect too much of this 100 close to 180 Hertz. So yeah, in fact, it's this way. It's close to 180. So yeah. So if the system weaker, then worse of the stability. Okay, so that's the first part of the show. Just showing, yeah, this capacitive stuff is no good. Let's go to the second part of the stuff showing the subcycle over voltage and AC over current and hydro 180 Hertz oscillations. All those are real world events, real life events. Let's say subcycle over voltage are the main cause of these two main events. 2017 Canyon 2 event, solar tripping, 2018 solar tripping, main cause. AC over current is this San Fernando disturbance is the main cause. And in the literature, we can also search IEEE power delivery. I think in 2018 published a Hydro One's paper by Chester Lee. There are a couple of events documented. One of them is showing this guy, 20 Hertz oscillation showing in the voltage RMS, and then 80 Hertz showing in the phase current. So we just call it Hydro 1 80 Hertz oscillations. So all these three events, you will see there's some commonality that is all related to solar PV being capacitive. So the first event is the AC over current. And basically current and voltage, from this figure, we can see that this current is having the relationship is minus Y multiply VG. The Y is the admittance viewed from the grid voltage to internal, including the network plus the VSC. So we will use just a simple sort of like a assumption of the VSC control structure, which is documented in this paper. It's ABC for NPR controller. So the control is looking like this. This is the control's impedance based on the PR controller impedance. So if this KR, this, the controller gain is smaller, then you can see it is impedance is much smaller of the VSC. By the way, you don't want the impedance to be small. In fact, usually you want to design stuff, you want to design the impedance to be larger. So small, then let's see what will happen. And by the way, here from 60 Hertz to about 1000 Hertz, that's capacitive. Now let's look at total Z from the VSC plus Z network adding together. Not only there's 60 peak at 60 Hertz, but also because of the network is IL circuit, then you can see there's a dip. That is at more than 60 Hertz, about 100 Hertz, let's say. And this dip becomes what this is. This is a dip. Basically, if you look at some dip in impedance magnitude, this look like a series LC resonance, sort of like. But you can view this like this. So you can see that series LC at about 100 Hertz, and if we flip it, it is admittance. This is admittance. Then there's a peak. So if you look at that, then the smaller gain invites a larger peak. And this peak basically says that when we have a disturbance, then there's about 100 Hertz overshoot in the AC current. And if the gain is smaller, then higher shoot. So based on this set of the figure showing that the overcurrent is happening, it is because something that this capacitive stuff, make it like capacitor, then this is LC resonance, and then we will see something that is peak, okay? Okay, the second example is a Hydro One, and again, we can sort of like view it as, before we view this guy as LC resonance, but this one we can also view it, can we just looking at it and think this is sort of like LC resonance, ILC resonance, So the system description is like this. This is a distributed feeder about 20 Hertz per damped oscillation showing in the RMS voltage. And the system is a 44 kV distribution feeder. At a substation, it is connected to a 30 MVA capacitor. And the capacitor in the morning, it will be energized, it will switch it in. And at that side, there will be 30 megawatt, total 30 megawatt MVA solar PV plant connected there. So there's a tube filter, there's a feeder about 30 kilometer length. PUC at here, the approximate photo level is 120 MVA. So based on those, you can set up the entire system's parameters using per unit values. And then what Hydro One observed is that there's like 20 Hertz here, and then a large 80 Hertz component, not only 60 but also 80 Hertz here in the phase current. And the phase current is pretty large anyhow. It's about 70% of this fundamental component. All right, so also provided by Chester Lee, thanks to him, that he gave this booty plot, is the FFT plot of the phase current to show that is this 60 hertz, there's this 80 hertz dominant one. There's also like a 40 hertz slightly. So 80 hertz will map to the 60 hertz. So basically, yeah, this 80 hertz will show us the 20 hertz. And the anyhow, that's another mirror frequency you can show it later on because of the converter stuff that you will show this. So if we keep looking at that, I think a little bit, we can just ask this question. Does it look like a series LC resonance at 80 hertz with grid being L and PV being C? So if we have certain like experience of the series LC resonance, we kind of think, yeah, it does look like this, especially at 80 hertz, we can even calculate approximately impedance is 0.25, seems like it's minus 27. So there's a dip again. You can expect if we plot this impedance of the entire network, you can see a dip at 80 hertz, right? So with all this information, second case. Third case, let's look at the justification why we can think. So this is the second case we can think solar PV perhaps has a capacitive component. Now the third case, subcycle over voltage, the Kenyon 2 event based on the nuclear report, page 18, it says, this study should also identify why the observed inverter terminal voltages are much higher than the voltage at the point of measurement. So overall, this system, previously we can show this is a shunt capacitor and the system inductors, this kind of resonance. But again, this one you have to think more. That the POM inverter terminal voltage much higher than the point of current voltage. Why? We have to ask this. So let's keep moving to looking at our previous study. In our previous study, we just do a very simple assumption to show that PV is the current source, and there's a shunt compensation, there's a grid inductance. So if we have the current source quickly ramp down, we can see that the voltage at the PCC bus at the capacitor will shoot up. And that is the LC resonance. We can just use the equations to accurately describe this. This is about 180 hertz subcycle voltage shooting up. And the yellow one is the grid, not changing, but the blue one is the PCC voltage. You can see it definitely shoot up. Okay. Now the question is that we have assumed that shunt compensation is put directly at PV. But in reality, it is not, because at the PV, it's called PCC bus. PCC bus to the POM, the substation, there's a transformer. So this topology, number one, it did not give us why the inverter, you cannot use this topology to explain why inverter voltage is greater than the POM, because this is POM, this is the inverter. So we have to separate do a better modeling to capture these details. Let's do a better modeling for the topology. Have the PCC voltage, PV bus, and the substation bus POM separated by a transformer or some other inductance because of the collecting system. And then we will put the capacitors there. So suppose the PV is just a current source, then if there is disturbance ramp down, we should expect the capacitor's voltage will shoot up. That this is what usually should happen. Subcycle or over voltage will happen resonance most severe in the capacitor. But it says that this voltage is more. So one reasonable justification is perhaps we can think that is shunt component because PV contributes that. PV itself has this shunt component. So let's do a quick check. I will put a shunt capacitor here and compare this voltage with this voltage just using circuit, this very simple circuit, do a quick check. I'm checking this guy input as the current input, current source, output as the 2 voltage, and put this blue versus the red. Blue is the PV bus, red is the substation. And if I put it as a capacitor in the PCC bus, then the PV bus has more severe over voltage. Very good. Then if I change this shunt as a capacitor as the inductor, then I should accept PV bus has less severe voltage. So using this justification, this quick example, we should expect to see the if based on real world hint, then this PV again should be having some capacitive component. So all these three cases basically indicate PV, solar PV is capacitive at a certain frequency range. And this has been verified by the reals measurement as well. Now we have more confidence. We can create a couple of numerical cases to do further like demonstration in this case. So here, first demonstration is about sub-cycle over voltage. We will cover two demonstrations. The first demonstration is sub-cycle over voltage. The same thing, this is PCC, then the substation, then we'll put the capacitor there. The VSC, then we will put the controllers there. For example, either it is ABC frame PR controller or DQ frame PI controller. Put some delay there and ignore the outer loop, ignore the PLL, just looking at the current control loop because we are looking at a subcycle very high frequency, like more than 150 Hertz. So it's okay to just consider the current control versus some circuit dynamics. So let's look at the PCC bus voltage, looking at the PV as the impedance. So move forward, both PI, PR, we can calculate that using similar current control bandwidth at 225 Hertz. Let's do a plotting. And delay is 100 ms. So plotting is like this. So let's take a quick look at the 60 Hertz to about 300. Here it's about it's 100, 2, 3, 4, 5. Yeah, about this way. This is all capacitive. And at the 150 Hertz from here, this is both capacitive and negative resistance. So that's PVC impedance. So that's the construction to show this. So with that, let's show the overall calculation, just looking at the, again, current order to the PCC voltage. And of course, we should also show the current order to the substation bus as well. So here I just put the PCC bus, and looking at the left, there is impedance. Looking at the right, we call the grid. So let's first calculate this VPCC, the body plot from I star to VPCC. This part requires a little bit of calculation. So this is YPV, the blue one, and this is the grid. So you can, the grid is green one. I think grid is green one. So if these two add together, then we can see the red one, right? So once this red one add together, and we can calculate what is VPCC versus this guy. VPCC should be, yeah, and I think it is, anyhow, this is related to this total and something related to this one. So anyhow, let's look at voltage order to the PCC. We can see the peak is at about 180 Hertz or 150 Hertz, 11.8 dB. And current order to the V substation, it is about 4 dB. So that's a huge difference. Not super huge, but 7 dB. That's significant, pretty significant. So if I ramp down the current order, I should expect to see much more severe over voltage at PCC voltage instead of substation. And by the way, I have given the parameters for the impedance, and the shunt compensation here. Finally, let's go to demonstration. That's the exciting part or easy understanding part. So I'm just going to plot the grid voltage, PCC voltage, substation voltage, and the current. So current is this guy, current order. I think this is what I plot. Yeah. All right, grid voltage, current order, PCC voltage, substation voltage. Grid voltage will have a dip, 10%. Current after 0.02 seconds, current order ramp down to 0. So now the PCC voltage should first have some dip, then you can see immediately to see the over voltage 1.53 per unit. Substation, then you can see 1.18. So this demonstration basically proves or just demonstrated why PCC bus will have more. That is because solar PV is capacitive. Let's look at what if scenario. What if the current control has no feed forward unit? Then we don't see over voltage. Of course, feed forward, these are all related to the design. What if the system has no shunt compensation at the POL substation? And then we expect to see less severe overvoltage in the inverter. In the substation, we don't see anything. So that's some of the study, just a demonstration, quick demonstration to show, yes, we have found the reason why the PCC bus, the inverter observe much higher overvoltage compared to the substation. So it's because solar PV is capacitive. The final demonstration, the one last demonstration is just to show the Hydro One's 80 Hertz oscillation demonstration. So we are going to again use the same test bed. This is a very good test bed that you can keep using. This time we're going to construct some barometers and to demonstrate 80 Hertz. And the first try is to make sure this ZPV will meet Z grid. Total grid is the green one. And the red one, yeah, green one is without shunt capacity, red one is with shunt capacity. They only differ when it is like in the 200 Hertz above range. Below, that seems like all the same. 80 Hertz, they're exactly the same. So that's why we cannot say this is related to the shunt capacitor. It's just the energizing of the shunt capacitor sort of like trigger this dynamics. So make this ZPV, can tune the control parameters and make this ZPV hit this grid at 80 Hertz. And at that time, you can also see because the PV is capacitive, it is capacitive and the grid is inductive, then they have a large phase angle difference about 180. And then that means there will be oscillations. So we're going to plot the total impedance, add these two impedances together. Then that's what we see. At 80 Hertz, there's a dip. So that means LC resonance again. Without the shunt, you always have this dip. A little bit sensitivity analysis, if we reduce the grid impedance, it's better for stability. If we have a larger proportional gain, better for stability, but I guess we are not interested to keep reading that. Let's look at simulations. We'll create 3 simulation cases to just looking at 80 Hertz and a little bit on the PL effect. So first case, yeah, so this time we are going to use a complete test bed that we not only with the current control, but with the outer loop control as well, and PLL. So all these PLL will be in. So first case, PLL bandwidth is 13 Hertz, and the current control parameter is very similar to the one that we have constructed, and the delay is 150 µS. So this one we are going to show mainly interaction of the current control and the circuit will generate 80 Hertz oscillations. Then the second case, we move the PL bandwidth a little bit higher, and the current PR controller again much higher. So this way we will make sure this interaction of the PLL, well, mainly PLL and current control will generate 20 Hertz in DQ. And then you can see both 40 Hertz and 80 Hertz in ABC. So that's for just a comparison. And finally, we're going to tune down the PLL bandwidth and tune this PR controller slightly better, sort of like an increased gain. And we're going to show both 40, 80 Hertz, but more like Hydro One's observation that 80 Hertz is dominant, 40 Hertz is slightly there's something. Yeah, so these two are sort of like 2 extreme cases, but this one is slightly in between, but more aligned to the case 1. So that's a circuit. And by the way, this is the method of SimScape, GUI. Very easy to use. VSC put it here. Chuka filter, then which one? This is the transformer to, then we have PCC bus. PCC bus, they have the feeder, and then we have the shunt compensation, that's substation. After substation, that's the grid. All right, so controllers are not dominant presented here. So case 1, going to just see 80 Hertz. So you can see this is the IMSF value current. Oh, by the way, dynamic event basically switch this guy in, switch the shunt capacity, same as the Hydro One's event. Looking at the IMS voltage 3-phase, you can definitely see 20 Hertz, right? IMS current definitely see 20 Hertz. Looking at the phase current, then what do you see? Okay, this is very nice curves. Looking at FFT, then both voltage and the current, you can see this THD, total harmonic distortion is much compared to the voltage. Voltage you see almost, it's very similar. I think we just captured maybe 2.1 to 2.2 like this couple of, or maybe capture like a couple of several cycles to get this. Anyhow, looking at that, this is mainly dominant. This is 80 hertz, right? And in fact, it's 82 hertz. Right? But this is just the dominant is 80 hertz. Just to see 80 hertz, there's nothing left aside. So this 80 hertz then reflected in RMS value, then you show 20 hertz. So that's why we call it 80 hertz, because it is mainly the static frames interaction called 80 hertz. Right? So if the PLL effect is dominant, because we can tune the PLL up and tune the current controller, also improve that, so it will not relate to it's not the interaction of the current controller, it's the interaction of the PLL versus the dominant guy. So now you can see, yeah, it's again 20 hertz if you just see this guy's 20 hertz. But if you look at the phase current and the phase voltage, look at FFT, now we are going to see both 80 hertz and both 40 hertz. They are comparable. So if you look at 80 hertz, it's not just 80, it's 80 and 40 comparable. Let's look at the case 3. Current control is again dominated, but the PLL can also play a role. Now we see 20 hertz again in RMS value, but we looking at the phase current, it is very similar like a case 1. But if we look at PLL, FFT, then in the current you see 80 hertz and 40 hertz also showing up. So this case is slightly more, well, it's not slightly, it's more like the Hydra one's observation, right? So anyhow, we can basically say that Hydra one's case is, you can make a little bit of the plausible justification to say, okay, we have demonstrated Hydra one cases. Majority, the dominant cause is the current control. PLL also plays a role. So as the concluding remarks, after we did all these studies, let's just coming back. What we trying to say, or what we have found? We have found that solar PV's characteristic being capacitive has played quite a role in those dynamic events. And why solar PVs are capacitive? That is because the current control employ PI or proportional resonant control that can lead to the capacitive impedance in this kind of frequency range. And this fact is widely known by power electronics people. Now the power system people looking at that and found if the impedance is pretty small, then this is inviting trouble, let's say this. So anyhow, this characteristic plus another one, negative resistance, and maybe small, the small impedance as a total, it can lead to these 3 events that we have just discovered, or we have just investigated. Okay, so that's all from this set of slides. Thank you.